Hello everyone and welcome back to this lecture series on renewable energy policies, regulations, grid integration and energy storage in India. So this is the second lecture of the series. In the first lecture, we discussed the climate change and need for renewable energy. So basically through this lecture series, I will be giving you an overview of the growth of RE and energy storage in India and the associated information. So this is all about me. I am Dr. Vipin Kumar. I am a deputy director at the central government, and this is all about me. It is also to declare again that the views expressed in this lecture series are personal and in no way they represent the view of the government. So this is the overview of the course. There has been a little change as discussed from the first lecture. So the area is also very dynamic. This renewable energy and energy storage, lot of changes are going on. Similarly, in this course also there will be changes, but that will be informed. So I have conceptualized four lectures for the series. First one was on climate change and growth of renewable energy. This second one, the present lecture, will be on the need for grid scale energy storage. So basically, we will be discussing what is the need for energy storage. Okay, so let us move on. So in the last lecture, we have seen that RE is important. Renewable energy, RE means renewable energy. It is important to mitigate climate change. Now, this renewable energy, it has inherent integration challenges while integrating to the grid. So the first one is we will discuss only major issues here. First one is that the major RE sources, which are solar and wind, they are intermittent and variable. So what is intermittency? Intermittency means all of a sudden it can go up, it can go down. Like in a cloudy day, the sun solar energy vanishes, and the solar and wind is also variable. That means that throughout the day, its intensity, the solar intensity is similar to the wind and speed. It is not constant and it varies. So what happens is that due to this fluctuating solar and wind, the voltage levels as well as the frequency levels of the generated electricity, it varies, it fluctuates. So this can trigger blackout, or this can trigger auto shutdown. So it poses a threat to the grid where it is connected. So concentration of RE plants in a particular region poses threat to the grid security. There is a recent incident which happened in Rajasthan. So that I will discuss in some other lecture. That a lot of grid was blacked out due to this large RE. Second problem with RE is that it impacts the fossil fuel generators in a way that when the solar energy is more, so that I will tell in some other lecture that this renewable energy, it has a must run status. It means that the whatever renewable energy is generated, it has to be supplied. So if renewable energy like solar or wind, it is more, then and our requirement is fixed, then we have to back down some sources. So RE cannot be backed down, then in that case these thermal plants, they are backed down. So when it is back down, it leads to wear and tear, stress, and thermal vibrations into the plant, which reduces its life. So these are major issues. Other issues are also there, like the renewable energy. It does not provide any reactive power. It cannot support the base load. It has low capacity utilization factor. Then this low capacity utilization factor was discussed in the previous lecture. Other issues also we can discuss in detail. They will come in some other lecture. If you want any particular issue to be discussed in detail, you can comment that in the comment section. I will try to clarify those into the next lecture. Then the renewable energy, it also leads to underutilization of transmission lines because generation is not fixed. So whatever the maximum generation is there, for that transmission lines are designed. But when the renewable energy generation is less, in that case, these transmission lines are underutilized. Further, the renewable energy that does not give any inertia support. So there is long-term decline of the system inertia also. So these are the challenges with respect to the renewable energy integration into the grid. I have tried to explain few, and if you need detailed discussions on other issues, you can just point it out in the comment section. I will try to explain them in subsequent lectures. Now, how to overcome these challenges to facilitate the integration of renewable energy into the grid? So the key is flexibility. This flexibility needs to be at the supply side, grid side, as well as at the distribution or demand side. So flexibility at supply side is there. We have that through the conventional sources. So like thermal plant, they can be backed down. So we have flexibility at the generation generating it in terms of that we can increase or decrease the generation. Now, flexibility at the transmission side or at the grid side, that is also required, and that means the amount of energy which is flowing through the grid that that we should be able to control. Similarly, it should also be controlled at the demand side. So this left side shows that the at present we have flexibility at the supply side. In future we want flexibility at the supply side as well as at the grid side as well as at the distribution side. So what are the ways through which this can be achieved? So this table summarizes the various various ways in which this can be achieved. So we have supply side flexibility, then we have grid side flexibility, demand side flexibility, then we have system wide flexibility. In that, you can see that the storage that will help for the grid side flexibility as well as the overall system wide storage flexibility. These issues can also be discussed in detail. So let me know what you want to discuss. If you want me to explain anything in detail in the subsequent lectures, I will try to explain them. Briefly, we can discuss like in the supply side, we have decreasing variable renewable energy generation uncertainty. So with advanced generation forecasting, so if we have better weather forecasting systems, we can have better prediction of the renewable energy. In that terms, we will have to deal with less uncertain variable renewable energy generation. Further, flexible generation should be there from the generating sources to accommodate variability from other sources. Now, at the grid side, there can be interconnections and regional markets as flexibility providers. So, if we have regional markets, then the excess energy that can be supplied to the market. Similarly, if there is deficiency, that energy can be purchased from the market. Now also we have matching RE generation and demand over large distance with super grids. If we have super grids, large grids, so at a certain pocket we will have more generation, but demand will be less. So demand can be more at some other pocket. So the region where generation is more, that region can supply the energy to the region where demand is more. Now, large scale storage. So, that already discussed. If we have storage at the transmission end, we can store the excess energy and supply it during the deficiency of the electricity. Demand side flexibility. So, there is aggregating distributed energy resources for grid services. So, distributed energy resources, what it contains. Uh, most of it is the this solar plants, rooftop solar plants. So they are distributed, they are not aggregated at one place. So if we can aggregate that, then we can have some electricity which can be supplied to the grid during its requirement. That will help in demand side flexibility. So similarly, demand side management can be done. So this is a broad topic. If you want to discuss it, let me know. I will explain it in the subsequent lectures. Then we can have RE mini grids for providing services to the main grid. So small mini grid can be there with renewable energy like solar and wind. Next, we can have optimizing distribution system operations with distributed energy resources. So basically, what it contains is that we can optimize the distribution system through our distributed energy sources like small solar, small wind is there. So we can optimize the distribution system with that. Then, if you need its example, I can explain that with examples. So just let me know if you need any topic in detail. Then system-wide storage flexibility, utility scale storage solutions can be there, power to X solutions. So power to X is another broad topic. So power to X basically means this power is converted to any X form. That X form can be converted to power or may not be also converted to. So this power can be utilized for to generate, create some other X element compound or source which can be used for other sources like green hydrogen, so or hydrogen. So that is an example of this power to X solution. So just let me know if you want to discuss this in detail. So these have been the overall broad overview of all the story of all the solutions we have for RE transition integration at present. Now our focus is on storage. So storage is there at present. So storage, this can provide this can mitigate frequency fluctuations. So storage basically provides the active power support, and if the inverter is having a reactive power support capability, then the storage can also provide the reactive power support. So the inverter basically it contains inductance capacitance circuit which generates the reactive power when it is required. Now it is also important to mention STATCOM. STATCOM is also basically an LC circuit, inductance capacitance circuit, which provides the reactive power support to overcome the voltage fluctuations. Now in our country, we basically have pumped storage project and battery energy storage systems. In battery also, we have mostly lithium-ion battery storage systems at present, and sodium ion is also under research at various IITs, but it is not commercially deployable at present. There are other benefits of energy storage systems in addition to the above this supporting frequency and voltage. Other benefits are firming up of RE sources. So whenever RE is fluctuating or intermitting, this storage can back it up so that we have a firm power from the RE source. Then if we are having a firm power, then the transmission network that can be designed for optimum utilization. So we already know this is the amount of power which is going to travel or at all the time. So we can design the transmission network for that power. Then we have enabling transmission and distribution capex deferral. So we don't need to increase the capacity of transmission or distribution systems, as the excess power will be stored in the storage solutions, and it will not be required to be transmitted or distributed. Then we have arbitrage also. The arbitrage basically means that the we can earn some revenue by utilizing the fact that this energy, the power from the energy storage will be different at two instances of time. So at off peak times the storage power will be cheap, and at peak times the storage power will be more. So we can store the energy during off peak times, and we can supply it to the grid during peak times. Then through an example I can tell, like in RK Puram area, The cost of electricity is 20% cheaper during off-peak hours, and it is 20% higher during peak hours. So we will have a 40% difference if we are using a battery to supply peak hours and charging it during off-peak hours. Then peak shifting and peak shaving, it can also be done through energy storage systems. So basically it is that during peak hours we will supply the electricity from the energy storage systems. So these are the various other benefits of the energy storage system. If you need, again I will request you, if you need any detailed explanation of this, just let me know. I will make a detailed discussion in the next lecture. So let us move on to the next thing. The various energy storage technologies, they have been broadly classified into six categories. There can be more categories. It is just a broad classification. So we have thermal energy storage, mechanical energy storage, electrical energy storage, then electrochemical energy storage, chemical energy storage, and hybrid energy storage. Now, so thermal energy storage means that the energy will be stored in the thermal energy form. Mechanical means in the mechanical energy form, that is basically kinetic and potential. Electrical means in the electrical form. Again, electrochemical means electrochemical, and chemical is this is in chemical form. Hybrid is a mix of this. So let us have a brief and short description, or detailed description is not required. So thermal energy is basically sensible heat, latent heat energy storage, thermochemical energy storage. You would have definitely studied about these broad terms in your chemistry classes in 11th, 12th. If you want detailed on this, you can just message me, but it is not required. You can search these on the internet. So sensible heat is basically storing thermal energy by heating a substance and keeping it hot for later use. Latent heat, you all know, change in the latent state without changing the temperature. So, and thermochemical energy storage is the method of storing thermal energy by using a reversible chemical reaction. So endothermic and exothermic reaction is used for this. Now, electrical energy storage is basically electrostatic energy storage and magnetic energy storage. Electrostatic is basically voltage, so capacitor and supercapacitor falls under this category. Magnetic is using the magnetic energy. Then mechanical energy, as already told, it is basically potential and kinetic. So pump storage project. This is an example, important example, because in our country we have basically, like earlier told, two types of storage at present, which is deployed in large scale. One is pump storage project, other is the battery energy storage, which will come later. Then we have chemical energy storage. So chemical energy storage stores energy in the bonds of atoms and molecules, while thermochemical energy storage, which we saw in the previous slide, that uses chemical reactions to store it. That is the basic difference between chemical and thermochemical. So name is similar, but this is the basic difference. Now electrochemical is there. So we have lithium ion battery that falls under this category. So I again got a little bit confused. Electrochemical is there, then chemical is there, then thermochemical is also there, right? So electrochemical is basically chemical reactions that produces electricity, like the batteries. So flow battery is also an important example. It is very promising, but at present its efficiency is very low. So it is not able to participate in the tenders which are floated for energy storage systems, and also it is not economical at present. So the tenders which are floated, they are basically technology agnostic. That is, every technology can participate in this, but at present the maturity and commercially economical are these batteries only. These two things only. One is pump storage, other is lithium ion. So mostly all the projects are from them only in our country. So thanks to you. Thanks for listening to the lecture. If you need any detailed discussions, like I told, please comment it in the comment section. I will try to make a detailed discussion for those in the subsequent lectures. Okay, goodbye. Thanks a lot. Bye.